anyhow we are, let's just start, and people will begin to know that we want to start at 4 and close at the time that we are supposed to close. Okay. So I tried, we and some of our colleagues that are working in the area of numerical analysis, we thought it to, try to organize this seminar series where we can invite researchers that are experienced to come teach us what they have been working on, and how they can, stimulate new ideas from our upcoming researchers. So I want those of us that do not have a PhD to take this seminar series. Very important, because I believe that, you will find some new direction and some people that can help you to also improve yourself in your research. So I want to thank some people that have, been with me since I started this this cluster. And one of the first people I remember I spoke to was Dr. Demba, who is our speaker today. He has been with me, and we have been sitting down to actually organize these lectures, from now till about July. We already have very good speakers that are going to speak to us. And there are some other notable professors that I got to discuss with. Professor Okongai from University of Benin. I spoke with Professor Bazwaye from University of Port Harcourt. Then my supervisor from University of Lagos has been with me, and has been my backbone, to encourage me to try to start this research cluster. And I remember I also reached out to the director of SIMPA to also, help me to get speakers too at some point, because I know that sometimes there might be shortage of speakers, and there might be sometimes that we need some specialized speakers, because I noticed that the area of numerical analysis that most people working in numerical analysis in Nigeria is tailored towards multi-step and block multi-step, the continuous linear multi-step, and I'm trying to see how we can diversify and try to begin to, work in some other areas. So even though you are specialized in block multi-step, you can still try to diversify and move to other areas. And this is just the goal, and also to encourage our researchers to be able to be open to several areas of numerical analysis, because, like I used to say, numerical analysis is the bridge between mathematics and scientific advancement. Because you need to solve problems, and most of the problems you are trying to solve are very complex, and we need numerical analysis to be able to provide solutions to these problems. So if we equip ourselves and we are very good, and you have the skills to be, you have the skills to be very competent to solve problems, then definitely that's prosperity for you. So I want all of us to take this seminar series, very important, especially in fact, this seminar series, the dream is actually for the students, the masters and the PhD students, to get as much as they can from this, and also to share ideas with people, link up with people, and try to meet people. You can use the chat box to meet people that you have been longing to see before, and maybe you find them here, talk to them, and try to create that contact with them, and then different things can come out. You don't know where you can meet with people. Like, for example, yesterday I joined the forum yesterday, and I met Luigi Bugnano. I know many of us here have cited Luigi Bugnano, but we've never met him. So, and he has agreed to be one of our speakers in the coming month, and he's going to speak with us in the coming month. So let us try to make this seminar series very, very important. Then I'd like to thank everybody. I can see the director of NMC here. I saw him just now, but I just want to appreciate him for joining us. In fact, for me to see his name here, that shows that he is really willing to also contribute to the advancement of mathematics in Nigeria. And I'm trying to see how best we can, take numerical analysis to the next level. And if you are a professor here, please, I beg you to please encourage your students, and we can all grow together. There's a lot we can do with numerical analysis, and I believe that it's not doing well in Nigeria. That's just my thinking. That it's not doing well in Nigeria, and we can try to diversify and help ourselves to be great. Then this is not a group. In fact, I didn't try to create a WhatsApp group. I don't want to create a WhatsApp group where we keep seeing popping up messages. It's not a group. It's not an association. That's why I'm just collecting emails by the form. So if I'm going to post the form in the chat box later. Maybe you can try to fill the form so that we can harvest your emails and also can regularly send you the notification to our programs. So everything, all communications will be through email, because I know we all have several societies and associations that we all belong to. So I'm not trying to create a new one. So it's just a place where we can, share ideas, meet people, have lectures, and go. Okay. Then if you have problems, of course, once you link with the potential collaborator, you can just continue to collaborate. So at this stage, I will call on Ms. Festa to read the bio sketch of the presenter. Our presenter today is Dr. Demba from the Aliko Dangote University. Okay, Ms. Festa, over to you, please.
Good afternoon, everyone. So I'll start.
So mute yourself.
Yeah. Can we all hear me?
Yes.
All right. Dr. Demba received a PhD degree with distinction in applied mathematics from the King Mongkut University of Technology, Thonburi, Bangkok, Thailand, under the Pestra Panjom Pleu Doctoral Scholarship. He's a recipient of the Extraordinary Award, Best Graduating Student, from the Faculty of Sciences, Department of Mathematics, University of Malaysia, for his master's thesis on trigonometrically-fitted explicit Runge-Kutta-Nyström method for solving special second-order ordinary differential equations with periodic solutions. He has published a considerable number of articles in both Scopus Index and ISI Web of Science Index journals, which are categorized as either Q1 or Q2. He's currently a lecturer in the Department of Mathematics at Aliko Dangote University of Science and Technology, Wudil, Kano, Nigeria. His research interests include numerical solutions to initial value problems of ordinary differential equations and, in general, techniques in numerical analysis. Thank you.
Okay, so I'll just stop sharing my screen. I was trying to pop up the agenda now. So after the citation, can we have Dr. Demba to give us his presentation?
Thank you, sir.
You may share your screen, sir.
Yes. Hope you can all see my screen, right?
Yes, sir.
Yes, sir.
Thank you. So good evening, everyone.
Good evening.
So let me just go straight to the topic of discussion of today. So the topic is a trigonometrically-fitted, diagonally implicit 5-4 pair of Runge-Kutta-Nyström method to solve oscillatory systems. So I will start by considering the problem and its solution, the nature of its solution. So I don't need to say much about my bio. So let me start with the nature of the solution to the problem in question. So the problem in question is a special second-order ordinary differential equation in which its solutions are oscillatory. By special second order, I mean the problem of the form y prime prime equals to f of xy, in which the first derivative doesn't appear explicitly. So that's why the problem is a special case of the general second order ODE. So its solution is oscillatory in nature, meaning it has this form, a transverse wave form, in which the direction of the traveling of the wave and the direction of the vibration of the medium are perpendicular to each other. So as you can see here, we have a red line in which it represents the exact solution to the problem in question. And the other colored line here is that of the approximate solution. So as you can see, there is a gap here in which we all know that the distance, the maximum displacement of this wave from the mean position here is what we call amplitude. And we have the peak here, which are the crest, and below here are the trough. of the wave, in which we all know that the distance between the successive crest or trough of this wave is what we call wavelength. So our goal here is to solve the problem in such a way that this gap, which we call dissipation error, and this gap, which we call phase error. So if it is possible to nullify these errors so that the approximate solution will be almost equal to the exact solution. So that's the goal. So the main goal here is not to nullify the dispersion and the dissipation error. So the goal is to use the trigonometrically-fitted method to minimize the gap between these two solutions. So these are the outlines of our today's presentation. The first is introduction, basic concepts, construction of the new pair, order of convergence, numerical examples, discussion, conclusion, acknowledgement, and references. So the construction of an efficient and robust numerical method to solve numerically the initial value problem of the second order ordinary differential equation in which the first derivative doesn't exist of this form, whose solutions exhibit an oscillatory behavior where Y is an RD and F such that R cross RD mapped to RD are assumed to be sufficiently differentiable, has over the years attracted the interest of many researchers. So this interest is due to the vast applications of the model considered in so many areas of sciences and engineering, such as quantum chemistry, fluid mechanics, physical chemistry, astronomy, and lots more. So to solve one, numerically, the family of Runge-Kutta-Nyström chords has been usually considered. Why? Because we all know that if we are dealing with a first order ODE, we use Runge-Kutta method because it is designed for that. As for second order ODE, yes, you can use Runge-Kutta method, but you have to reduce it to a system of first order. And by doing so, automatically the efficiency of that method has been reduced. So we don't want that. We want to derive a method that will solve it directly without the conversion. So that's where the Runge-Kutta-Nyström method will play a vital role. So related with such use, different methods of the class of diagonally implicit RKN methods have been studied by so many researchers. As you can see, they have been cited. So recently, Demba et al. In 5 and 4 constructed 2 new embedded pairs of DIRKN methods of orders 5, 4. The first one having constant coefficients and the other with variable coefficients and of phase and amplification fitted type for solving the problem in one. So you see, we considered phase fitted and amplification fitted type to derive an embedded 5-4 pair of diagonally implicit RKN method, in which the one we are talking about here today is an advanced form of this, the phase and amplification fitted type. So in this study, we construct an efficient diagonally implicit adapted RKN 5-4 pair using the trigonometrically-fitted technique in variable step size to solve the problem in one. So the derived method can solve accurately the usual test equation, which is of this form. So the numerical experiments bring out the performance of the developed method compared with some diagonally implicit embedded RKN methods appeared in the literature. So to the best of our knowledge, there is no other trigonometrically adapted DIRKN method in the current literature. So an implicit RKN method with R stages is generally expressed by the formulas. this which approximates the solution, and this is that of the derivative of the solution, where yi here is given by this formula. So this is the general form of a Runge-Kutta-Nyström method. So where, as usual, y sub n plus 1 and y prime sub n plus 1 denotes approximation, denotes approximations for y of x sub n plus 1 and y prime of x sub n plus 1 respectively. And the grid points on the integration interval of this are given by the formula, this, where h is a fixed step size. So the above implicit method may be formulated compactly using the Butcher table. So instead of writing the formula 2 to 4, you can just use this table, where C here is a vector of coefficients, A is the matrix of the method, B transpose and D transpose are also vectors. So A here is R by R matrix with entries Aij, which is a lower triangular matrix. Of coefficients with Aij equals 0 for I less than j. So that's the definition of an implicit method. A method is said to be implicit if the coefficients of the matrix Aij are 0 for I less than j. And if you have, in addition, the diagonal entries of your matrix to be the same, then that's when we have diagonally implicit Runge-Kutta-Nyström method. So where this is a vector of stages and this also. So for short, the method in 2 to 4 can be written in this form. So an embedded type MN pair of RKN methods comprises 2 of such methods, one given by this with order M and another one with order N, which is of this form. So they both share the coefficients C and A, in which N is less than M. That's the order of the first method is bigger than that of the second method. So we put the 2 methods together. That's the embedded. So you put the lower order method within the higher order method. So the method of higher order provides the approximate solution, this and this, while a second set of approximate solution is provided by the method of lower order, which is of this form. We use cap to present that. So this second approximation is obtained just to provide an estimate of the local truncation error. So a pair of RKN embedded methods may be expressed by the Butcher table below. So this is how the 2 methods have been put together to form an embedded method. You have CA. If you take this and this, you have the higher order method. This, together with this, you have the lower order method. So in this work, we consider a variable step size approach on the basis of a local error estimate provided by the embedding procedure. So the local error estimate at this point is obtained through the differences. So based on the solutions we obtained from the higher and the lower order methods, we obtain this and this. So next, we find the maximum of these norms. So in which this denotes the local error approximation to manage the step size or the step length h on each iteration. So in order to advance the solution of the problem in hand, we use the step length control strategy presented in 16, which is given by this formula. So this is where the variable step size approach takes place. So being told here is a tolerance selected by the user. P here is the order of the higher order method considered. And 9/10 here is just a safety factor. So if EST sub n plus 1, which is our local error estimate, if it is less than the tolerance, then the step is accepted, and we applied the accepted procedure of performing local extrapolation, meaning that the more accurate approximation will be used to advance the integration. So if the EST sub n plus 1 is greater than or equal to the tolerance, then the step is rejected and H will be updated using this formula. So next is the definition of a trigonometrically-fitted RKN method. An implicit Runge-Kutta-Nyström method, as given in the equations 2 to 4, is said to be trigonometrically adapted if it can integrate exactly a second order problem with a set of fundamental solutions, e to the power of I omega x and e to the power of minus I omega x, where omega here is the frequency of the problem considered. So applying the RKN method in 2 to 4 to the test problem, so we obtain this, where y1 is given by this, y2 is given by this, up to yi is given by this. So let us assume that the exact solution of the test equation is given by this. So we compute the values y sub n plus 1, y prime sub n, and y prime sub n plus 1, and introduce them in the equations of the method 5 to 9. So if we use the Euler's identity, which is e to the power of iv equals to cos v plus I sin v, and compare the real and imaginary parts of this, and this, respectively, we get the following systems. So this is the trig-fitted RKN method. So we have to integrate the problems using this. So where V here is the speed, we can call it the speed, which is given by omega h. So from the nature of the problem we have, which is oscillatory in nature, each problem has its frequency, and for the h is the step length. I here is the imaginary part, which is the square root of minus 1. So next is the construction of the new pair. So in this section, we will derive an embedded 5-4 diagonally implicit trigonometrically-fitted RKN method. So to achieve this, we first construct the DIRKN 5-4 method, which is that of constant step size method. I mean the constant coefficient method first. So which is diagonally implicit 5-4 embedded pair of constant coefficients with 4 stages. So to derive this pair, the order conditions up to order 5 of the RKN method has to be considered together with the simplifying assumptions. So these are the order conditions of the Runge-Kutta-Nyström method up to order 5. The reason why we put order 6 here is to calculate the principal local truncation error. You need one order more than the order of the method you derived. So that's why I had to include the order 6 here. So the first part is that of the solution, and this is for the derivation. The derivative of the solution. So all subscripts I, J, K vary from 1 to R. Most methods requires the CI to satisfy the following. So we need this to simplify the number of equations. So if you are deriving a higher order Runge-Kutta-Nyström method, so you need also this simplifying assumption. You need this. So to obtain the 5th order method of the embedded pair, we have to solve the system of equations of the order conditions up to order 5, together with the simplifying assumptions given in 25 and 26. So this gives a system of 21 equations with 18 unknowns. So to some, they will say this cannot be solved. Why do you have less number of unknowns? I mean, why don't we have equal number of equations and unknowns so that we can solve it easily? No. You may have underdetermined or overdetermined equations that are overdetermined or underdetermined, and you may have a solution at the end. So we utilize Maple software for that. So if we fixed C1 to be equals to 1/10 and C4 as a free parameter, we obtain a 1-parameter family of RKN methods whose coefficients are, so these are the coefficients of the method of constant coefficients. So for C4 equals to 1, we obtain the coefficient of the 5th order 4-stage DIRKN method of the embedded pair as given below. So these are the coefficients of the 5th order method of this embedded pair. So the coefficients of the principal terms of the local truncation errors, that's the PLTE of the main formulas of the above method to approximate the solution and the derivative are given by this. As you can see, this indicates that the method is of order 5 because you have P plus 1 here. So to derive the 4th order formula of the DIRKN54 embedded pair, we utilize the lower triangular matrix A and C of the 5th order method derived above. So we have to utilize C and A. So we consider the system of equations of the order conditions up to order 4, together with the simplifying assumption as given in equation 25 for R equals to 4. So we obtain a system with 12 equations in 8 unknowns. And taking C1 equals to 1/10, we obtain a 1-parameter family of methods whose coefficients are this. So for B4 equals to half, we obtain the coefficients of the 4th order 4-stage DIRKN method of the embedded pair, this as given below, with the coefficients of A and C common to both of the two methods. So the coefficients of the principal terms of the local truncation errors, that's the PLTE of the main formulas of the newly obtained method are this. So here we have 5, which is the same as 4 plus 1, meaning the order is 4 here. So the coefficient of the DIRKN54 embedded pair is given below. So these are the coefficients of the derived method of constant coefficients. If you consider this, and this, you have the higher order method. If you consider this, and this, you have the lower order method. As you can see, you have embedded pairs now. So to obtain the adapted RKN pair, we take the coefficients of the lower order method in the DIRKN54 pair. Now we have to solve the system in equation 10 to 13, taking 4 of the coefficients as unknowns. So specifically, we considered B1 cap, B4 cap, D1 cap, and D4 cap as unknowns, and obtained the following values. So when V goes to 0, I mean, when V approaches 0, so these coefficients, when V approaches 0, we are going to, I mean, the initial method, I mean, the original method, coefficient of the original method will be retained. So the method coefficients of the 4th order adapted method become the constant coefficients of the counterpart method in the DIRKN54 approach. So similarly, for the fifth order method, if we consider as unknowns B1, B2, D1, D2, in the equations 10 to 13, we obtain the following solutions. So again, when V approaches 0, the above method, the above values of B1, B2, D1, and D2, in case of the higher order adapted method, become the constant coefficients of the counterpart method in the DIRKN 544 pair. So the new adapted DIRKN method, embedded method with the above coefficients, depending on V, and the remaining coefficients of the DIRKN 544 method will be named as this. So this is the new trigonometrically-fitted, diagonally implicit Runge-Kutta-Nyström 5-4 embedded pair. So next is the order of convergence of the derived method. So this part is devoted to prevent the local truncation errors of the formulas of the proposed method and to get the orders of convergence. So the local truncation error, that's the LTE for any DIRKN method, is given by this, where we know how to obtain tau 1, tau 1, 2, tau 1, 3, tau 1, 4, tau 1, 5, and tau 1, yes. So we know how to obtain this. They are the principal, the PLTEs. So the lower order adapted RKN method obtained in the previous section has a local truncation error given by this. So as you can see here, all the coefficients of the LTE up to V to the power of 4 vanishes, meaning that the method is of order 4. So from which we can infer that it has algebraic order 4. So the higher order adapted RKN method obtained in this section has a local truncation error given by this. And as you can see, the coefficients of this LTE up to V to the power of 5 vanishes, meaning that the method is of order 5. Next is the stability of the method. So an interval from this to this corresponding to the RKN method in equations 2 to 4 is said to be an interval of periodicity. If for every H tilde here, H cap in this interval, so if the modulus here of the eigenvalues is 1 with the two eigenvalues not equal, then we say that the interval is that of periodicity, where this is the characteristic equation. So using the maple package from the above definition, we get that minus 2.01 to 0 as the interval of periodicity of the fourth order constant coefficient method in the DIRKN 544 pair, and this is that of order 5. So similarly, from the above definition, we get that this is the interval of periodicity of the fourth order adapted method in the TF DIRKN 544 pair, and this is that of the order 5. So next is the numerical experiments. So to evaluate the performance of the derived method, we consider some standard pairs of RKN methods for numerical comparisons. So the first one is the one constructed as the diagonally implicit Runge-Kutta-Nyström method that is derived in this work, which is of constant coefficient. And the second one here is also the adapted method derived in this work. Next is the one derived in this paper. The paper that has been cited in this. Next is the one that is here, which is of phase fitted and amplification fitted. Next is the one derived by read eta in this. Next is the one derived by imoni eta in this. Next is the one derived by senu eta in this. So the above methods will be used to solve some well-known oscillatory IVPs. So they have been implemented in the C programming environment using a PC with 2.3 gigahertz processor, Intel R, Core TM, i3, and with a RAM of 12 gigabytes. So we first considered an orbital problem of this form, in which we integrated this problem over this interval from 0 to 10 with a known solution, which is the exact solution as this. So in order to use the adapted schemes for solving this problem, we have considered the frequency as 1. As you can see, what we have here, omega x.
Back after presentation. I have to say more.
So here we have omega x. So omega here is 1. Same here. So that's why we considered the frequency of the problem as 1.
Please unmute yourself. Sorry.
Hello?
Yeah, we can hear you now.
So for the adapted methods, we have taken omega equals to 5, which is the frequency of the problem. So the obtained data are collected in table 2 and 3, considering different tolerances. So the tables contain the number of steps, that's n step, the number of function evaluations, that's NFE, the number of rejected steps, that's R step, the maximum absolute errors, that's max ER, and the computational time in seconds, which is CPU in second. So we can see that the proposed method presents very good results concerning the number of steps and computational time. So as you can see, considering this tolerance, the derived method, which is TF DIRKN 544M, solve the problem within this number of steps. That's 24 steps. As you can see, the rest, they have so many steps. So the same with the gap between the two solutions. That's the maximum absolute error or global error. So you see, it is also minimized. The computational time here is 0.055 seconds, which is less than the rest of the methods. Same with this tolerance. We have 58 steps here. The number of function evaluation, 582, which is less. And also the time here, the computational cost is being minimized. So same with the other tolerances. And for the other problem we considered, as you can see, the number of steps is also greatly minimized. The number of function evaluation has been minimized. And also the computational time is also the least. So to further show the robustness and efficiency of the proposed method, we present the efficiency curves of TF DIRKN 544M compared to other existing DIRKN pairs. So if you go 2 and 3 show the efficiency curves for the problems considered, where one can observe the good performance of the proposed methods. So we utilize the following tolerances. So as you can see, the one we have here, the one in black is the derived method, in which in the graph here, we have the log to base 10 of the maximum absolute error versus log to base 10 of the number of function evaluation per steps. So the one below here minimizes this and this. That's why it is the one below. So the derived method is considered the best for the problems considered. Same here. So the developed method presents high efficiency and accuracy when solving all the given modeled problems as shown in table 2 and 3 and in figure 2 and 3.
Hello, Dr. Demba. Hello?
Hello?
Hello, Dr. Demba. We can't hear you. Wow.
Well,
Okay, so I guess Dr. Demba is having some network issues. So maybe before he tries to join back, I think what he's trying to solve some problems of oscillatory problems, and these problems are problems that that normally, the solutions always have trigonometric functions of sine and cosine, and to get methods that solve this problem, you need some kind of specialized methods. And one of the specialized method of finding a way to solve these problems are trying to adapt numerical trig functions into Runge-Kutta methods, and that's what he was trying to do. And he was able to derive an embedded pair. When you say embedded pair, you have to work with two methods simultaneously. One is actually doing the calculation, while the second one is just helping you estimate, give an estimate to the actual calculation. So you use both pairs. The difference of both pairs tells you whether you have to advance solution or to go back to recompute the solution. So once you recompute the solution, right, if you have to recompute the solution, you are going to half the step size that you already used before. You half it by you divide it by 2 and run the simulation with that. So once you run it with that, you compare again, and once it accepts your tolerance, then you now double. So it's as if you didn't lose anything. So once you because you were not able to advance, you have to go back by dividing by 2. So once you divide by 2, right, and you now fit in your acceptable tolerance, right, you now have to double it, so double the step size for the next computation. So it's as if you have gone back to meet what you have left before. So that's how embedded method works. And this trigonometric fitting that is trying to infuse into this thing is what is trying to actually make the method very, very good. And I hope he can join us as soon as possible. I guess he's having a network problem, and he has tried to demonstrate these particular methods on some very interesting problems that exhibit those kind of solutions. So I think I have also worked in this area before, and although I did that for just the class of Runge-Kutta methods, and I think it's a very promising area that MSc students or PhD students, aspiring PhD students, can also take the challenge to try to derive methods in this direction. In fact, there are some class of symplectic RKN methods, and you can also try to infuse, also adapt the trigonometric fitting to it too. And that's a new area that maybe some people can take up. So I'll try to reach out to Dr. Demba and see what the problem is. Let me just try to reach out to him.
Sir, I have joined.
Oh, you joined back. Okay, thank you.
Yes, sir. Sorry, sir, please.
No problem.
Is the network?
It's fine. I know. It's fine.
Sorry, I don't know where.
Okay, so
am I supposed to continue with?
Yes, you are here. You're just here.
Okay,
Continue.
okay.
Yeah.
So also we have obtained the local truncation error for both the higher and lower order methods of the pay TF DIRKN 544M, showing that the order is preserved. So furthermore, the stability intervals for both the higher and the lower order methods have been computed. So from the numerical results, we can assert that TF DIRKN 544M pair is the most efficient among the DIRKN methods used for comparison. So with this, that's the end of my presentation.
Okay. Thank you very much, Dr. Demba, for your very interesting presentation.
Thank you, sir.
I can really say that I find it very interesting, and I know that a lot of us have learned one or two things from this from your presentation.
Thank you.
And I will just leave the floor for people to just make some comments and also ask some questions. Okay. But before that, maybe I will just give some time to I don't know if he's still here, to the director of National Mathematical Center to just give some comments before we start to take questions. Prof.
Thank you. Thank you so much. Can you hear me?
Yes, sir. It was breaking, but you can speak on, sir.
All right. Thank you so much for the well-presented seminar, and also the coordinator. I think it is quite interesting that somebody has to combine different numerical methods to solve a given problem. It's a very good one. Just as the coordinator said, it is an area that those that are exploring to be in numerical analysis can go into and come up with new methods of solving. And of course, these are problems that are very vital. And of course, when you consider our environment, most of the things that we see, they are natural. So we need to solve problems that goes beyond just the normal finite differences that we are using. Having said that, since we are dealing with numerical analysis and we're trying to compare with the normal method and other methods, since it started by displaying those graphs that they did, I thought I was going to, at the end of the day, though we have seen that, yes, the error is highly minimized, I was expecting I was going to go back to those graphs again to plot the two things together. I was expecting that, because since you started with that well, it is a oscillatory problem, and they started with that, trying to describe the wavelength, the troughs, and all that not. So I expected him to go back to plot that for us to see if they fit in or not. Thank you.
Okay, thank you very much, sir, for that. I don't know if Dr. Demba would like to respond to that before I now start taking questions from our participants or viewers or researchers.
Yeah, thank you so much, Prof. So, Prof, to verify that the derived method is really efficient? Yes, there are so many ways you can do that. One is the one you propose, that at least why not we plot that of the solution and that of the approximate, whether the gap is greatly minimized. Yes, by reducing the number of steps, reducing the number of function evaluation per steps, reducing the computational costs, it implies that as well. So there are so many ways to deal with that, that question.
Okay, thank you very much. So at this stage now, if you have some questions, you could just use the react button. You see a react button on your screen. Just react and raise up your hands. I'll call you as it appears. So just raise up your hand if you have questions. I will call as it goes. Okay. So the first question, we'll take question from Dr. Ibrahim or Professor Ibrahim Hassan. Please unmute yourself, Professor Ibrahim.
What is it?
Exceed now.
Oh, okay. What of Professor Buhari Al-Hassan? Can you ask your question?
Okay. Yes. Good afternoon to you all. I'm very happy for this kind of seminar that has been arranged by you, sir. And also, it is a well done and a very good presentation from Dr. Demba. Can you hear me?
We can hear you, sir.
Okay. So I have some comment, observations, and the question also at the same time. Normally we that are dealing with linear multi-step method, or in particular block backward differentiation formula and backward differentiation formula. What we will be doing is that before we develop a diagonally implicit method, we first have to go back to develop the fully implicit methods. So after we develop the fully implicit method, then we come and develop the diagonally implicit methods. So, and I see that like Dr. Demba, you have just developed an explicit, fully implicit Runge-Kutta-Nyström methods. What I want to ask now is that, is there a fully implicit is there any explicit, fully implicit Runge-Kutta-Nyström method that has been developed earlier before your diagonally implicit Runge-Kutta-Nyström method being developed? If there is, that fully implicit method that has been into existence and your method that you have developed are the two things that you should be comparing with. And secondly is that from your numerical results and the graph that you have plotted, you have said that you have plotted the graph of efficiency curves in which you plot the log of maximum error against the log of function, the log of number of function evaluations. So what I'm saying is that since we are talking about efficiency, because in numerical analysis we are measuring both speed and accuracy. Why you did not compare, and why you did not plot the graph of log of maximum error against the log of computation time? Because it's only when we plot that graph of log of maximum error and computation time, we will clearly see the efficiency. Of the methods. But notwithstanding, your method is good because it has reduced the computation time, total number of integration steps, and also number of functions evaluation. And also the next question I want to also ask is that why did you choose that substitute factor to be equals 9/10? To be equals 9/10. Why not, let's say, 1/10 or 1/10 or 1/2? Because we know that the substitute factor is restricted between 0 less than less than that let's say C is safety factor. So 0 less than C less than 1. It is between 0 and 1 and 0 are excluded. So this is what I just wanted to say, sir.
Okay, so let's just call Miss. So you just answer everything together. Let us call on Miss Ruth Olowe to ask her question.
Good evening, sir, and good evening, everyone. I want to thank our coordinator, Dr. Ige, for this wonderful program that he has, bettered for us in numerical analysis. God bless you, sir. And I want to thank our Dr. Demba for this beautiful presentation. I say also, God bless you, sir. So my questions, I have like 4 here. Number 1, I want to know the advantages of variable step method over fixed step method. That is, when we use the variable step method, what are the advantages that we stand to get over using fixed step method? Then the second one, I want clarity on the order of the method that you use, sir. I understand that you were using the newly proposed method to solve second order problem. But I am a bit confused where you were getting the order of convergence. That place where you were getting the order of convergence, the power there is 6, and you said the order is 5. I'm thinking it's supposed to be 6 minus 2, since you are solving second order problem. Then number 3, where you choose the omega, that is the fitting frequency, you showed us the coefficient of x in the problem. What if we have a problem that the coefficient of the x is not given? And then the last question is, can we say embedded method are the same thing as block methods? Thank you, sir.
Okay, so we have, so the last, so those are the people that want to ask questions. So Dr. Demba, can you react to these questions? And, Professor Al-Hassan, do you still have a question to ask? Professor Hassan. Professor Hassan Ibrahim. Professor Hassan Ibrahim, do you have a question to ask? Okay,
seems
Dr.
like
Demba.
maybe he's not. Yeah.
Dr.
So,
Demba.
yes.
Yes, sir. There is another question that I want to ask. So in this slide,
some of our questions. So I don't know whether maybe let me just take it one by one.
I think he just allowed Dr. Demba to
okay,
answers. Yes, thank you.
So she asked, there are 2 questions which, if I heard correctly, she said, what are the advantages of solving the problems using constant constant coefficient method or using variable coefficient?
No, yeah. Sorry, sir. My question is the advantages of variable step method over fixed step method.
Yeah, I say the same thing.
Okay.
Please proceed. Please proceed, Dr. Demba. Hello, Dr. Demba. Dr. Demba, I guess it is a network problem. Okay, so maybe I just try to also cover for him before he comes back. Dr. Demba, are you there? Hello, Dr. Demba. Okay, if I heard some of your questions correctly, So, Dr. Olowe, so you asked them the advantages of, Dr. Demba, are you back? The advantages of variable step size and the constant step size.
Yes, sir.
So you know that sometimes, for example, you are solving problems with that has to do that maybe problems with waves.
Okay.
And for example, you know that if you go with wave with let's assume wave with discontinuity, for example. So you have it that it is not really, there's a kind of a break such that you have where you have like a square wave, for example. If you use fixed step size to solve such problems, the fixed step size does not really characterize the dynamics of that system, because by the time it gets to the place where you have the discontinuity, where you have the sharp bend up there, so, a square wave now, a square wave has something like square, square like that looks like square, square is breaking like a square. By the time you take constant step size and you get to that place where you have to take that sharp bend, the constant step size will continue to, simulate the problem as if it is straight. But for the variable first step size, once it gets to that place, if it computes the result at that particular place where you have that bend, the error between the solution and the estimate is going to be very wide apart, which will be greater than the tolerance that you have. Then that will give you an alarm, raise an alarm for you to reduce the step size. So you keep reducing the step size until it adapts itself to that dynamic, to the original dynamics that you are looking at. So by the time it crosses that part where you have that discontinuity, then you can now double the step size to continue your simulation again. I don't know if you understand that kind of that trick. Okay. So that's one of the advantages of the variable step size, because you can it actually has to take each step as it goes. So each step must be correct with respect to a particular tolerance I have given. So you want the error at this step to be less than 6, 0.10 - 6. It must be before you move to the next point. If it is not, it must go back.
Okay.
But for the constant step size, it just continues to run the simulation till you get to the end of the simulation.
Okay, sir.
Yeah.
The
so
second
question is which one? What again?
The order of convergence. He said.
So for RK methods, how you define order for RK methods is quite different from multi-step methods.
Okay.
So for multi-step methods for second order differential equation, we know that it has to be P order P plus 2, right?
Yes, sir.
For second order methods, right? But yes, for Runge-Kutta method, what you are just comparing is the expansion of the exact solution and the numerical solution. Okay. So you just make sure that everything is at par up to the place where you get the truncation. So the last place where you get the truncation determines what the error of the method is.
Okay. Then can we say that embedded methods are block methods?
Not really. You see, there are two different things. You can use, when two things are going together, we can say they are a block of implementation. But in the context of our block methods that we do here, where our block means that you have several points, you are trying to calculate, you want to get numerical results at several points. So we call it a block of implementation. But in this particular case, you can only get value for just 1 point, which is yn plus 1. So the two methods are calculating yn plus 1. The first one is calculating yn plus 1. The second one is calculating yn plus 1. The second one is just an estimate of the first one, but it's just the same thing you're calculating.
Okay.
Yeah. So I don't know if anybody here has any other thing to say. Maybe just to, before Dr. Demba joins us, maybe just to add to this discussion that we have. I can see Professor Akombi with us here. So maybe he has something to also add. My dean, sir, and my Oga from undergraduates. Prof, sir. Prof. I don't know if you have anything to add. Any other person, if anybody has anything to add to this. Prof, please, do you have anything to add to all this discussion? Anybody has anything to add?
Yes, hello, Dr. Ige.
Yes, sir. Yes, sir. Oh, my Oga, Prof, you're welcome, sir.
Thank you.
Yes,
2 things.
Yes, sir.
Just as you explained correctly, in a layman's language, when you use variable step method, when you are far from the solution, it doubles its steps as if it is running towards the solution. As he's getting there, he knows he's getting close. He won't run at the speed at which it was coming. It will start moving gently in arriving there. But that is not the area I want to contribute. I want to contribute in the area of the one particular question that the first person asked of, and that is the use of log error in determining the efficiency. That is an old procedure now. The more reliable way is the efficiency curve, especially where you want to compare the capacity of many methods as to choose the most efficient one. The best way now, there are theories backing that one up. There are analyses backing that up. But in a nutshell, for the purpose of this meeting, it is sufficient to say that just go for the efficiency curve. By the time you go for the efficiency curve, you will see the efficiency of each scheme as to determine which scheme is more efficient. And I think that was the target of the presenter.
Thank you, sir. Thank you, Dr.
So
Demba.
I'm
Thank
sorry,
you very
sir.
much. Dr. Demba is back. Yes.
I'm
so
sorry.
we tried to answer some of your questions, Dr. Demba. So
Okay.
maybe you just concentrate on the answers of the first speaker, the first person that asked questions. We have answered the second person.
Okay.
Yeah. So the man that talked about the full implicit and explicit and all those things. I don't know.
Okay.
Maybe just try to respond to that person. Yes.
But I did not jot the question.
Oh, the question. Okay, so
I was
I
unable
think
to do that.
So maybe I give him another space to ask his question again. Is it
Please.
Professor Alassane? Professor Alassane, are you here? Okay, I think he's left. But he's still online, but I don't know. He's okay. So do we have any other contribution that we want to say or any observation? Oh, Mr. Abdul. Professor Abdul.
Good evening, everyone.
Yes, Professor Abdul.
Yeah, am I audible?
Yes.
Yeah, let me first thank the presenter for the nice presentation and the organizers of this seminar. I have two questions, actually. And one of the questions is, the presenter, I didn't see anything that has to do with the convergence rate of your method. Also, why did you implemented the method for numerical experiment with 2 test problems only? So what is the justification to say that this method is efficient for solving these problems because you're considering only two problems? I feel they could be selective.
So can I respond to your question?
So please, Dr. Demba, you can just respond to that.
Yeah. We did not consider only 2 problems. It is not only for the sake of presentation that I only pick 2 problems out of about 7 problems that I solved in the actual paper. So you're not expecting you to bring all the problems we solved. It would be like, it will look somehow even to the audience. I mean, they will not feel okay with it. So I only consider 2. That's it.
Okay,
thank you very much.
But in the actual paper, we have so many problems.
Yeah. Thank you, Dr. Demba. I think you have answered that question very well. This is just for presentation's sake, and I believe that, for presentation's sake, you just have to keep things easy. You don't have to put so many problems here. Not everybody here are numerical, so you don't want to bore people with so many things.
Yeah, I understand. But at least we could have perhaps a dollar and more performance profile to show the result in a better way. You don't need to put the problems, but you can display using one graph will suffice. If you understand what I'm talking about, the dollar and more
we understand. But as numerical analysts, what we always like to showcase those things, and but your point is well noted, sir.
Thank you very much.
As for the convergence, you said, right?
The convergence rates.
Yes, the convergence, that's the order of convergence. The order of convergence is the one we derived, in which I explained.
Yeah.
If your derived method is able to retain the order of the original method, so meaning the method converges.
Nice.
As I explained, as you can see, the local truncation error, so that V power of 5 with regard to the method of order 4. So meaning all the coefficients of V up to all the coefficients of the LTE up to V to power 4 vanishes. So meaning what is left is V to power 4 plus 1, which is P plus 1, meaning the order is being retained.
Oh,
So
thank you very
that's
much.
the aim.
Thank you very much, Dr. Demba.
I have one.
Sorry.
I have one last person that wants to ask, Professor PC.
Sorry, please. Dr. Demba, thank you for that explanation.
Thank you, sir.
I realized that you also solve some linear systems of equations, and I was wondering, that could be a point of collaboration. What method do you usually solve these problems? And how large do your dimension get?
Are you talking of linear system?
Yeah, I saw something like you have some linear systems at the end of the day.
We are not solving linear systems.
Sorry, no
We are not
linear
solving...
systems, not linear, no linear systems.
You mean non-linear ODEs?
Non-linear equations, non-linear equations. I think
no, they are not. They are non-linear ODEs.
Okay, Professor Nedu. Professor Nedu, you have questions?
They are non-linear ODEs, not non-linear system.
Yeah.
System of ODEs.
All right, thank you very much. Thank you very much.
Okay, the system of ODEs.
Professor Nedu. Professor
Okay.
Nedu.
Good evening, everyone.
Good evening, sir.
Julius, thank you for putting this together. And Mr. Presenter, thank you very much for your presentation. I just want to make two comments. You know, you derived your method, and you also derived the order of the method, you know, which is 4, the local truncation error, according to your presentation there. But the thing is, for you to really verify and convince yourself and your reader that your method is of so and so order, then you must have numerical experiments. Those results that you presented, you must have experiments that show that this method is of order 4 or of order 5, as the case may be. So I would suggest you look that up, because that is when you do that, it tells you more than one thing. Number one, it convinces you that the method is truly of that order. Number two, it convinces you that the implementation of the method is correct. So that is even the first thing that must be done before comparing the method with any other one or checking the performance of the method, because at that point, you know that, yes, my method has been correctly implemented. The code I'm using is doing the right thing, and the order that I have derived has been verified computationally. That is number one. Number two, you know, the tables you showed in one of the ones I saw, the table you showed there, you put the CPU time for each method, the CPU time consumed by each method, and you also put the you also put the maximum error. And if you look at the maximum error there for different methods, they are different. They are not the same error. So then that means that it's not achieving the same result. It's not for the thing to do is you set a maximum error you want to reach for all the methods, and then you check the CPU time that each method is going to consume to achieve that. I don't know if that point is clear. Since I'm going.
Yeah.
Okay.
I understand.
I think I'll just react. I'll just
Okay.
Dr. Demba, will you allow me react a bit?
Yes,
just a
sir.
bit.
Yes.
Okay.
Yes,
So, Professor Chinedu, but it has been my brother for a very long time. What you are saying is you are very, very correct. you know, but I just believe that, you know, this is just for the sake of presentation. And I know that Dr. Demba is an experienced and a very, you know, is an expert in this area. And I know he knows what to do in presenting what you have just said. So maybe you know, I'm sure in the paper, because I've seen some of his paper, I know that most of the time, you know, just like what Professor Chinedu said, you know, so if I want, all the methods must attain 10 raised power 6, and we are now trying to look for the time all of us try to reach 10 raised power 6. So that time determines what the computational time of, also we cannot measure our efficiency based on that approach. And I think that Dr. Demba already, you know, took note of this. Dr. Chinedu.
Yeah, I'm fine. I'm okay. Yeah.
Thank you very much. Yeah. Professor PC. One Professor PC is there. I don't know your name.
Yes, I can hear you, sir. Can you hear me, sir?
Yes.
Yes, sir. Yes, I want to thank you, Dr. Hige, for coming up with a seminar like this. My question is, because my own area is infectious disease modeling, and I've seen so many numerical approaches that have been used in solving this method, like Runge-Kutta. I've seen a lot of them. So can I adopt this method to solving non-linear epidemic model? So that is my question, sir.
Yes, sir. Yes, you can. It depends on the nature of the problem you are solving. Yes, it's an ODE, I believe.
Yes, it's an ODE, yes. Non-linear ODE.
ODE may be of second order, right? Or first order.
Yes. But all this one, they have initial conditions.
Yes. You need to know the order first, so as to know the right method to apply on that.
Yeah.
So definitely you can apply.
So is there an algorithm for that? Can I mail you personally? Can I have your email?
Yes.
Can I get you personally? Yes, after this. Okay.
Why not?
Your email was written in that flyer. Please, Dr. Demba, please, can you type your? Okay, can you just type your email to? Maybe, yes, just type your email on the chat box, maybe.
Thank you very much, sir. That is my question. Thank you, sir. Thank you, Dr. Ige.
Yeah. So maybe I just leave. I will ask. I don't know if Professor Akombi is still with us here. I don't know if you can hear me, Professor Akombi. Okay, he's not here. Okay, Professor Adekunle, are you still here with us, sir? So any other question before, before we leave? Any other question before we leave? Prof. Okay, Professor Akombi is here. Okay, maybe we just allow Professor Akombi give us some words of, before we leave. Professor Akombi, sir.
All right, Dr. Julius, thank you very much. I thank you. I thank the presenter. Mine is not a question, actually. I'm in a place that is very noisy, so I have to step out to connect with another device. I just wanted to encourage all of us on this platform. This is long overdue. This kind of a thing is long overdue, and I really want to appreciate Dr. Julius for taking the initiative. We are just, I think, currently now 51. We're at a point we're 60. There are a lot of numerical analysts all over Nigeria. Let's reach out to them so that we can continue to encourage one another and tackle challenges that is confronting us in the field and taking up live problems, solving, providing solutions and the likes, including people in the applied mathematics. So I just wanted to encourage all of us on this platform. Thank you. Dr. Julius, thank you. It's a job well done. The seminar is a success. God bless you all.
Thank you very much, sir. Okay, so we're already drawing to a close because I want us to always close by 5, latest 5:30 we should be out. So I just want to give announcement that in the coming next month, we'll be having a talk from the director of CNRS in France. So he will be giving us a talk with one of his newly graduated PhD students. So we'll be giving us a talk on some applications of numerical analysis in biology. Then in April, we'll have somebody from Italy. In May, we will have somebody from Uniben. In June, we will have somebody from Rivers State University of Science and Technology. Then in July, we have Professor Luigi Bugano. Bugano will be taking us in July. So let's just try our best to just keep it up to always. So we'll be holding these meetings every third week of the month, Wednesdays, the third Wednesdays of the month, from 4 to 5:30. Latest 5:30 we should be here. So if you have any comments, I have put on the chat box our LinkedIn page. You can follow the LinkedIn page. You can check the chat box now. The LinkedIn page is there at the beginning. I can repost it again if you missed it. So, and also we have a form where you can fill to give your information. If you just join, maybe you've not filled your form and we don't have your email, because we'll be using the email to communicate with everybody. So I don't intend to form any WhatsApp group. So all communications will be through email. So if you want to receive emails from me, for reminders of our programs, then you can just try to fill this particular link that I've put on the chat box. So before I leave, I don't know if anybody has any comments, suggestion, or anything you want to just say before we go. We still have about 8 minutes to go.
Well done, Dr. Zelos.
Yes, sir.
Okay. Mine is an observation as I.
Prof, we can't hear you again, sir. We can't hear you again, sir.
Can you hear me now?
Okay, yes, we can hear you.
Can you hear me now?
Yes, sir, Prof. Go on, sir. We can hear you, sir. We can hear you, sir. Okay, does other person have any other comments? Any other comments? Okay, I put on the chat box also my personal email address, and the email address I'll be using to correspond to send emails to everybody now. So you might want to just write it somewhere, and it's on the chat box now. So for information on the chat box, our LinkedIn page, try to follow our LinkedIn page. Then also fill the survey form where we can address your email so that we can continuously send you emails. Then I've put my email there, and also the email that I'll be using to send message for this research cluster. Then maybe before next week, I'll try to open a YouTube account where we can put our lectures. So from next week, this lecture, I'll try to quickly sort that out and put this lecture on the YouTube page. So in the absence of no question or comments, I want to thank everybody for coming today. And I believe that next week will be a very interesting time. Sorry, next month will be another interesting time for us to meet again and share ideas. I thank you very much for being a part of this first one. And I pray that the Almighty Lord continue to, meet us at the point of our needs and in our research, and give us ideas and connections for us to be able to advance the scientific world. Thank you very much.
Thank you, sir.
So bye-bye.
Bye-bye.
Yeah.